Good evening, everyone. Today's class, I will start with chromatographic techniques. It is essential that you know these basic techniques and the basis of chromatography before we go into high performance liquid chromatography. So, with this slight change, I'll talk about chromatographic techniques today, and I will continue with the high performance liquid chromatography in the next class, which is either Monday or Tuesday. So, if we start with chromatographic techniques, now first let us understand what is chromatography, what are the basics of chromatography techniques, whether it is the planar chromatography, that is paper and TLC, or is it the column chromatography, which involves both the high performance liquid chromatography and gas chromatography. So, what is chromatography? It is a technique which is commonly used in laboratories to separate mixtures of compounds into their components. And once we have separated them into their components, we can analyze them, identify them, further purify them, and also quantify them. So if you look at this mixture on the left-hand side here, it has a mixture of three components. By using the technique of chromatography, we can separate this mixture into the four individual constituents. And that is what chromatography is all about. So, chromatography is a separation. Let us look at some history on chromatography. Who discovered chromatography? Chromatography itself means the technique to separate and visualize substances. It actually, if you translate it, it actually means color writing. Who coined this word color writing? It was a Russian botanist by the name of Sweat who actually discovered chromatography, or who was the pioneer of chromatography. And what he did, his initial experiments dealt with plant pigments. He was trying to separate the plant pigments by using a column of chalk. And since the plant pigments were colored, they separated into different colors, and he called this color writing. So it was Svet Nikolaev Simonev, who is a Russian botanist, who is the pioneer or the discoverer of chromatography. So what did he do? He actually used a technique which was a liquid absorption column. So he took a glass tube, filled it with calcium carbonate or chalk, put a ground plant extract on top of it, and then he allowed it to develop with some solvent, that is, the solvent that he extracted the plant pigments with. And he saw that it could separate into different colors, and so he named this process as chromatography. Chroma in Greek meaning color, and graphy in Greek meaning writing. Literally, it means color writing. The actual surname of Nikolaev is Ubeev, which also means color in Russian. So there is a possibility that his naming the procedure as chromatography, color writing, was a way that he could make sure that although a commoner of in Russia, it would be immortalized, everyone would remember him for chromatography. So a very little bit on the history of chromatography. In any technique or any methodology, it is good to know from where it originated. So the uses of chromatography, they can be used to analyze, that is, to examine the mixture for its components, as was shown to you earlier. You can also use it to identify different components, For example, you can identify caffeine in coffee. You could identify the catechins in tea. You could identify theanine in green tea. You can identify chlorogenic acid in sunflower seeds. So any compound could be identified by this chromatographic technique. And generally, the chromatographic technique is used to identify organic molecules or organic analytes. They are also used to purify. When we do the overexpression of proteins such as insulin and the antibodies, they need to be purified, and they are all purified by a technique called chromatography, so that you get pure insulin or you get the pure antibody that you require. It is also used, chromatography can also be used to quantify the amount of an analyte or a chemical in a mixture. So chromatography is a versatile technique, as you will see, that you can use also different types of media. But what we need to understand is, first of all, some terminology and the general definition or a detailed definition of chromatography. So, chromatography is a technique that separates components in a mixture by using differential affinities of the analytes or the compounds for the mobile medium or for the stationary absorbing medium. Now let us look at what is or what are the meanings of differential and affinities. Differential means showing a difference or a distinctive difference between two compounds. So compounds are two different compounds because of their properties can be, because of their different properties can be separated. Then we have affinity. Affinity is a natural attraction or force between things. It is just like positive attracts negative, negatives repel each other, an enzyme is attracted by the substrate, an antibody is attracted or has an affinity to the antigen. So that is what affinity is, like the affinity of iron filings to a magnet. And then these two words are very important in all types of chromatography, that is the mobile medium or the mobile phase, which is the gas or the liquid that carries the components along with it, or and the stationary medium or the stationary phase. It is a support of the apparatus, which, as the name suggests, is stationary. That means it does not move. So the mobile phase moves and the stationary phase remains uh, stagnant or in one position. So the components of chromatography are the mobile phase, which is generally the solvent. But in chromatography, we don't call it the solvent, we always call it the mobile phase. And then you have the stationary phase, or it is the solid matrix or support. And the third is the analytes which you want to separate, which are called as the solute. So you have the mobile phase, you have the stationary phase, and you have the analytes in question. And these analytes interact differentially with the stationary phase, as a result of which they can be separated. So, a very simple example for you to understand the phases. So, here is a road in which you have a large number of runners participating in a marathon. So, from this, I'm sure all of you can tell which is the stationary phase. So, the stationary phase is the road because it doesn't move. The mobile phase are the runners because they are moving, and the attraction, differential attraction here is the way they put their foot down on the road. So the fast runners will be putting their foot down at a very fast pace, and the slow runners will have it at a slow pace. So they become the actual, the differential affinity. And what is the solute over here, or the analyte? The analyte is these large number of people, and we are going to separate them into the front runners, the middle runners, and the last runners, or the backbenchers. So here the solvent front, or the front line leaders, that is these who are in the front, are known as the solvent front. So in chromatography, we have the stationary phase, which we can compare to the road, the mobile phase, which we can compare to the runners because they are moving constantly, and the third is the solvent front, that is the front line, that is the leaders. And before them, you will not have any of the winners. So similarly, in a chromatography, in front or ahead of the solvent front, you will not be able to see any solute or any of the analyte. You should not see any of the analyte. Here is a second example of a sailboat racing, where you see that the sailboats are the mobile phase, the water in the sea is the stationary phase, and this finish line over here is the solvent front. Okay, so you have the mobile front, you have the stationary front over here, and of course you have the solvent front. So how is this technique of chromatography carried out? Whether it is a planar chromatography or it is a column chromatography, a mixture of the analytes is first placed on the stationary phase. The mobile phase is then passed through the stationary phase. The mobile phase solubilizes the components, and based on the affinity, the mobile phase carries the individual components of the mixture through a certain distance in the stationary phase, depending on their affinity for both the phases. So in theory, of the basics of chromatography tell us that it involves the separation of mixtures due to differences in their distribution coefficient, or what we call as their equilibrium distribution of sample components between two phases. So the distribution coefficient, or the equilibrium coefficient, is given by the formula concentration of the component A in the stationary phase divided by the concentration of the component A in the mobile phase. So the differential affinity of A for the stationary phase and the mobile phase now causes the separation. So remember this, it is the distribution coefficient. In many cases, it will be called the partition coefficient, and in many a time it might be called as the equilibrium distribution coefficient. In all these cases, the term is the concentration of component A in phase 1 divided by the concentration of the component in phase 2. So chromatography, as I said, is based on a physical equilibrium that results when a solute is transferred between two different phases, that is the mobile phase and the stationary phase. Now look at this figure where you have a stationary phase and you have the mobile phase, and you have the analyte A. At any point of time, some of the analyte A is attracted to the stationary phase, and some of the analyte A is freely available or freely moving in the mobile phase. So what is shown A is the analyte which is adsorbed to the stationary phase, and A, which is shown in black, is the analyte which is traveling in the mobile phase. So the distribution coefficient or the partition ratio K is equal to Cs by Cm, where Cs is the molar concentration of the analyte in the stationary phase and Cm is the molar concentration of the analyte in the mobile phase. So previously, in the previous formula, it just said concentration, but here we are very particular and we say it is the molar concentration of the solute in the stationary phase divided by the molar concentration in the mobile phase. So it is the differential affinity. So how many types of chromatography we do? We can divide the chromatography in two types depending on whether we use a column or whether we do not use a column or we use flat plates. So in column chromatography, the stationary phase is packed or held in a narrow tube through which the mobile phase is forced down either through pressure by using a pump or by gravity. Planar chromatography, on the other hand, the stationary phase is a support which can be a flat plate or the interstices of a paper, that is the spaces between in the cellulose molecules in the paper, and the mobile phase moves through the stationary phase by capillary action or by gravity. So the difference between column chromatography and planar chromatography is one, it is used in the column filled, the other is it is a flat plate, and common to both is the separation can occur by gravity, but the difference between the two is in column chromatography we can also cause separation by using pressure, that is using a pump, whereas in planar chromatography we do not ever use a pump, but it occurs through capillary action. So in planar chromatography, we can further divide it into thin layer chromatography, or commonly called TLC, and paper chromatography. As the name suggests, here thin layer chromatography is a stationary phase which is spread out in a uniform thin layer through which the solvent will pass or the mobile phase will pass. And paper chromatography is when the stationary phase is paper which is made out of cellulose. And in column chromatography, we have several types of column chromatography. We have got liquid column chromatography, where the mobile phase is a liquid, and this includes high performance liquid chromatography, ion exchange chromatography, affinity chromatography, size exclusion or gel permeation chromatography, hydrophobic interaction chromatography. So here the stationary phase, the interaction between the stationary phase and the analyte is based either on size or on charge or on affinity. And then we have the gas liquid chromatography, where the mobile phase is a gas, which is generally helium or argon, which is an inert gas. You must remember that in chromatography, the mobile phase and the stationary phase have to be inert to each other. The mobile phase should not react with the stationary phase, and the stationary phase should not interact. When I say interact, it means chemically act with each other. That is the solid support uh, which is there in the column chromatography. So what are the modes by which, or the mechanism by which these types of chromatography take place, or the forces that are involved in the separation? Mainly in planar chromatography, And in um, the column chromatography, it is by a process known as adsorption. So adsorption, as you know, is sort of sticking to the surface. And the most common adsorbents we use here are alumina and silica gel, which interact, which the interactions with the solute molecule is due to the OH groups on the surface, as you will see as we move along the class today. More polar molecules will be adsorbed more strongly and they will elute slowly. So the strength of the adsorption of polar groups on a polar support is of this order. And the olefins, the ethers, the esters, the lactones, the aldehydes, amines, phenols, and acids. So here the process of separation is adsorption, desorption, adsorption, desorption. So the analyte will adsorb to the stationary phase and it will dissolve from the stationary phase and go into the mobile phase. So the mechanism is one of the major mechanisms, especially for paper chromatography, planar chromatography, and for some column chromatography, is adsorption. The second most important mechanism through which the mode of separation is through what is known as partitioning. Partitioning of the analyte is based on the solubility of a sample between two liquid phases. Many of you might have used the separation flask or the separatory funnel to separate. So what you see over there is, depending on the solubility of the analyte, the concentration of it will be more either in phase 1 or phase 2. In partitioning also, here in chromatography, it is the partitioning of the analyte between the mobile phase and the stationary phase. Now you will ask me, it is a stationary phase. No, generally in the stationary phase, we have what are known as bonded phases, which are solvents which are chemically bonded to the stationary phase. So partitioning will occur between the mobile phase solvent and between the solvent which is bonded to the stationary phase. And we will see that when you see the structure of the gels. So the analytes will equilibrate between the two phases according to their partition coefficient. The partition coefficient is nothing but the concentration of the analyte in solvent 1 divided by the concentration of the solvent in analyte 2. So the higher the partition coefficient in the solvent, the higher the concentration it will be in. And then we have the separation based on charge. So here the separation based on charge is a competition of different ionic compounds for the stationary phase. The stationary phase can either be positively charged, called as anion exchanger, or it could be negatively charged, known as a cation exchanger. So if the analyte is negatively charged, it will bind very strongly to the anion exchanger and elute very late. If it is positively charged, it will not bind because it will be repelled. And in a cation exchanger, the analyte with a positive charge will be attracted to the negative surface, and the negatively charged particle will be repelled. So here the separation is based on charge. So if we see the separation of proteins on this cation exchanger, which is shown in gray, you will see that a protein which is negatively charged will not bind and will elute first, whereas that which is positively charged will bind and will elute much later. And these resins or columns are known as ion exchange columns. Next, the separation can take place based on size, and this chromatography is known as gel filtration, size exclusion, gel permeation, all these mean the same. The stationary phase here is generally a cross-linked polymer, and this polymer has got different pore sizes. And the pore size of the stationary phase or the matrix will dictate the degree of interaction. So what you see over here in this picture is that here is a matrix and it has got different pore size. So now if I put a mixture of these molecules of different size into it, the small molecules will enter the gel matrix. The large molecules being too large cannot enter, and so therefore they will elute or come out. So here the separation takes place in which the large molecules come out first and the small molecules come out last. Those of you who have used molecular sieves or who have used sieving in the kitchen, you know that we use the sieve to actually sieve any product such as an atta or as a rice flour. But there you see the small molecules come out first through the pore of the sieve and the large molecules remain in the sieve. So gel filtration or size exclusion is very similar to sieving in the kitchen. So here very well explains in size exclusion chromatography, we have a porous stationary phase. So the stationary phase generally is filled in a column and these have got definite pore sizes. The gels consist of open three-dimensional networks which are formed by cross-linking long polymeric chains of dextran, of saccharose, which are all polymers of carbohydrates. The pore size is dictated by the degree of cross-linking, and the diameter of the pores is the one which tells you which molecules will be excluded and which molecules will be included. So here is a method by which you can separate analytes based on their size. And then you have affinity chromatography, where the stationary phase is a phase which has bound to it either an antigen or an antibody or an enzyme. So the interaction between the two is due to an affinity, that is the biological affinity, and they can be excluded by changing the conditions. So affinity chromatography is the affinity of the analyte for the matrix. So those analytes, as shown in this figure, the blue analytes, the antigens, have very high affinity for the antibodies. And you see the other molecules, that is green and mustard, are non-antibodies. They will not bind. And then you can elute the bound antibodies with the antigen. Then you have a hydrophobic interaction. All of you must be knowing by now about the interactions that we have. You know, we have hydrogen bonding, we have van der Waals forces, we have ionic interaction, and we have the hydrophobic interaction. So hydrophobic interaction is an interaction in which the polymer matrix is highly hydrophobic, and if there is an interaction between the hydrophobic um, analyte, then you will see, because of hydrophobic interaction, that is like attracts like. So the hydrophobic interaction is involved in the separation. So we call this HIC, or hydrophobic interaction chromatography. So the two hydrophobic surfaces come together due to the hydrophobic interaction. Now let's look at, those are the mechanism of action. That is how separation takes place in chromatography. So separation, as we have seen, can take place by adsorption, can take place by partitioning, can take place because of the difference in charge, can take place because of the difference in size, it can take place because of the hydrophobic interaction, or it can take place due to biologic affinity. So now let us look at detail in planar chromatography, which involves both paper chromatography and thin layer chromatography. So in paper chromatography, this chromatography is a partition chromatography, which uses the filter paper strips as the inert support, and the solvent will be a mobile phase. The factor governing separation over here is it is assumed that in the filter paper, between the cellulose molecules that are there, there is some endogenous water, and so therefore the partitioning will occur between two immiscible phases. One is the water adsorbed on the cellulose fiber in the paper, which is the stationary phase, and the second is the organic solvent, which is going to be the mobile phase. So here the water of the cellulose is in the interstitial spaces. The paper as such is an inert support. So partitioning occurs between the mobile phase and the stationary aqueous phase, which is bound to the cellulose, and the isolation depends on the partition coefficient K of the solute. So the partition coefficient K is given by the concentration in the stationary phase divided by the molar concentration in the mobile phase, not very different or exactly the same as the distribution coefficient. So the general procedure for performing any paper chromatography is choose the paper, different types of paper are available, choose the solvent to be used, carry out the equilibration of the paper with the solvent, prepare your sample, apply the sample to the paper about 1 centimeter away from the edge of the paper, then put it into a chromatographic chamber and use either ascending or descending or radial chromatography or two-dimensional chromatography for the separation. The separation occurs because of the partitioning of the analyte between the mobile phase and the stationary phase, and then once the analytes are separated, they need to be detected or visualized, which can be done with different visualizing reagents, and then you identify the substances. And I'm sure all of you or most of you must have done paper chromatography at some time in your student career. So, in chromatography, what is important is a number, especially in paper chromatography and thin layer chromatography. This characterization of a number called the retention factor is very important because the analytes are identified or they are actually named by their retention factor, or what is simply termed as the RF value. The components in the sample, as you will see, will travel along with the mobile phase of the solvent to separate into bands for each component. So the retention factor is given as the ratio of the distance traveled by the solute from the original line, that is here, divided by the distance traveled by the solvent front from the original line. So mathematically, this is the expression. It is a ratio, so therefore it has no units because even if you measure in centimeters, numerator and denominator cancels out, it has no units. The RF of any solute cannot be greater than 1. Okay, the RFs will range anywhere between 0 to 1 and never above 1. If it comes above 1, then you have some contamination in the solvent because it is moving along with the solvent. So remember this word, retention factor, the RF value, and know how to calculate the RF value. So generally when we measure the RF value for a solute, we measure from the origin line to the middle of the spot, not at the leading front, nor at the um, front which is lagging behind. It is measured at the center of the spot that you see. So a wide variety of papers, that is the filter papers, are available commercially of different sizes, of different shapes, different porosity, thickness, and chemical treatments for paper chromatography. It is evident that we need this because we have to, the analytes that we need to separate are of a wide and varied nature. So, what are the factors you would consider to select the paper for your choice? The nature of the sample, the mobile phase that you are going to use, the thickness of the paper that you want to use. The thicker the paper, the slower it is. You know that capillary action will be very slow. The detection method, whether the paper will be destroyed by the method that you're going to use, and also depending on whether you want it as a qualitative method or as a quantitative method. Okay. Generally, in paper chromatography, Whatman number 1 is the world standard chromatography paper, and it is has a very smooth surface. It is about 0.18 mm thick, and it has a linear flow rate of about 130 millimeters per 30 minutes. The Whatman number 1 filter papers contain about 98 to 99% cellulose. There are various types of Whatman filter papers which are graded based on their thickness and based on their speed. So you have fast papers which are number 4, 54, 540, 31 and 17. You have medium flow papers and you have very slow papers. The fast papers are very useful for all the major applications and used when RF values are very wide apart. The slow papers are used for enhancing resolution, especially when two analytes move very close to each other or they have very close retention factor, that is the RF value. So, in the papers, you have different types of papers other than the Whatman paper. The Whatman paper, the Whatman paper can be modified so that the separations can be more, the resolution of the spots can be more, and a wide variety of compounds can be separated. You have the carboxyl papers, which are used for cationic separation and protonated amines. You have acetylated papers, that means there is a chemical treatment for steroids and pigment separation. You have silica and aluminum papers, alumina papers for low polarity molecules. You have ion exchange papers, that means papers to which the ion exchange molecules are bound. You have Kisalga papers, zirconia papers, and you have the silica papers. So these are specialized or modified cellulose papers that are available for specialized types of paper chromatography. So if you look at the chromatogram, after we have after we have spotted the analytes, you need to develop the chromatogram. There are four different methods by which we can do the developing, and that is either by ascending, that is allowing the capillary action to take place from bottom to up, or we can do it by the descending method or the radial method, and we also have a special technique in paper chromatography which is known as the two-dimensional technique. So when you see in a radial separation as seen over here for the plant pigments, you can see that they appear, the analytes will appear as concentric circles. Just let us look at the way these chromatographic experiments are performed. So in radial development, you have a circular filter paper placed on a trough with a wick from the center dipping into the trough. So through capillary action, solvent flows up, and at the analyte, the mixture of the analytes is spotted in the center, and as the solvent moves, it will move from the center. So the solvent front starts moving and the analyte gets separated. So this is known as radial chromatography. In the ascending development, you use a chromatographic chamber, you spot, and the mobile phase is kept in a trough, and the filter paper or the stationary phase is allowed to dip into the mobile phase. Because paper is very thin and it cannot support itself, we generally use a hook on the lid of the um, chamber through which the paper is suspended and the analytes will separate. So generally there are special chambers for the ascending development. A third method is a descending development, also due to capillary action, but the solvent from front moves from top to bottom. So we have a trough containing the mobile phase, and the paper is supported by a glass rod and dipped into the mobile phase so that it flows down the paper and the separation takes place. So you can use either a radial development or an ascending development or a descending development. Coming to two-dimensional chromatography, this is a special technique to use. It is used when the components of the mixture are very closely related to each other in structure and cannot be separated by either descending, ascending, or radial chromatography, and they need more than one solvent to be used for separation, more than one thing. So in two-dimensional chromatography, the sample is applied at one corner of the stationary phase or the paper. So the disadvantage of two-dimensional chromatography is you can analyze only one sample at a time, unlike the ascending and descending, where you can analyze a large number of samples and also can co-run the standards. So here in the standard paper, you spot the analyte and you run the chromatography in the ascending or descending mode in one direction. Allow the solvent, that is what is shown in B. After the solvent front has moved to the edge of the paper, dry the paper, evaporate all the solvent, and then rotate the paper exactly 90 degrees and develop it in the second solvent. So if this is the paper, you have run it this way, you turn the paper 90 degrees and run it in a second solvent system. So now you see in the first direction, this red and this spot have not separated, and these two spots have not separated. However, when you run it in this direction, in the second direction. So what you see is the yellow and the red have the yellow and the gray have separated, and the red and the pink have also separated. So now you have got a very good separation. So different types of solvents are used for in the two different directions. The factor that we must remember over here is the first solvent should be completely volatile, because after the first run it must be dried or evaporated completely. Then you have multiple chromatography, which is similar to two-dimensional chromatography, where you can develop it in a 2 to 3 different solvents. So you can develop it in the first solvent, some separation will take place. You can dry the paper and you can develop it in a second solvent or mobile phase, again dry the paper and separate it in a third or fourth mobile phase. So here the mobile phase one can use either the same solvent system, or you can use a different solvent system. So once the paper has been developed, either by these techniques, you need to visualize or detect the analytes. This is done by physical methods, that is exposing it to iodine vapors, and we know that iodine, all the halides, halogens will bind across the double bond to the and give you a color which is only physical, it disappears. So you can expose it to iodine and mark off the spots, or you can view it under UV light at 254 or 365 nanometers in a UV chamber. Chemical methods are destructive methods. The physical methods are non-destructive, so you can collect your analyte. But in the chemical methods, these are destructive, giving different colors. So you can use sprays, which are generally sprayed onto the paper and dried. Some examples are ferric chloride for phenolics and tannins, ninhydrin reagent for amino acids, which gives a purple color, Dragon drops reagent for alkalides, 3,5-dinitrobenzoic acid for cardiac glycosides, 2,4-dinitrophenylhydrazine for aldehydes and ketones, ammoniacal silver nitrate for reducing sugars, aniline diphenylamine for sugars, and resorcinol reagent for fructose and sucrose. A large number of chemical reagents which react because of the color reactions can be used. But one precaution that must be taken over here is that the spray should not destroy the paper. I mean, it should not eat up the paper. It should be inert to the paper. Now coming to thin layer chromatography, which is very similar to paper chromatography, but here the stationary phase is not the thin paper, but it is a thin layer, and it is a very useful separation technique. Although very old, it is still used extensively, and the advantage is it is quicker than paper chromatography, and you need relatively smaller quantities of the material. And now automation of the thin layer chromatography to high performance thin layer chromatography or HPTLC has made this technique even more versatile. So here the stationary phase is a thin layer of adsorbent. So it is silica gel, most commonly silica gel or alumina, which is coated on a solid support such as, or an inert support such as a plate or a plastic sheet or an aluminium foil. The mobile phase is the developing solvent which passes through up the stationary phase by capillary action, carrying the samples, and the components will separate based on how much they adsorb on the stationary phase versus how much they dissolve in the mobile phase. So if the affinity for the stationary phase is higher, it takes longer to separate. if the affinity to the mobile phase is greater, they move very fast in the thin layer. So the stationary phases that are commonly used as layers are silica gel. The mode of separation is by adsorption. It is very commonly used, and it can be used to separate a large number of compounds, including amino acids, peptides, aflatoxin. This is very important because for detection, we still use the silica TLC with silica gels, bile acids, vitamins, etc. Then you have the bonded silica gel. That means where the silica gel is chemically treated so that the interacting group is not the hydroxyl group of silica gel, but the amino group or the cyano group or the diol group or the reverse phase group, which could be carbon 2, carbon 8, or carbon 18. So in the amino bonded, the mode of separation is partitioning. In cyano bonding, it is partitioning either in the normal or the reverse phase. In diol bonding, it is normal phase partitioning, and in reverse phase, it is reverse phase partitioning. When I take the class on high performance liquid chromatography, I will explain in detail what is normal phase and what is reverse phase partitioning. But using these techniques, a large number of analytes can be separated in from their mixture. We also have aluminum oxide, cellulose, Kieselguhr, and polyamide. So here, once again, the mode of separation is adsorption, partition, or partition for Kieselguhr, and for polyamide, it is ion exchange. So you see, a cellulose stationary phase can be used for amino acids, sugars, alcohols, carboxylic acids, and fatty acids. So in the technique, in the bonded phases, as I said, the silica can be chemically modified. This shows you the structure of silica. So in ordinary silica gel, it is the interaction between the OH group and the analyte. In chemically bonded phases, this OH or the silica hydroxyl group is modified chemically. So what you get is chemically bonded phases, and the analyte interacts not with the silica portion, but with this chemically bonded portion. So the chemically bonded silica that are available, if this is the original silica, you have the amino bonded. So you see the reaction of the molecules is with the amino group. You can have octadecyl, that is the reverse phase. So the reaction of with the analyte is the interaction with the C18 part or portion of the bonded silica. You have cyano, so the interacting group is the cyano group, and you have the diol bonded silica where the interacting group is the diol bonded silica. These figures have been put to tell you that the silica as such can be modified. So among the silicas, silica gel is the most popular and versatile of the group. Just like Whatman filter paper is the most popular for paper chromatography, silica gel is the most popular and versatile for thin layer chromatography. The silica gel 60 angstrom is commonly called silica gel 60, and it is used for a wide range of separations in food analysis. The pore sizes of the silica will vary from 40 to 150 50 angstrom for commercially pre-coated plates. The changes in the pore size cause a change in the selectivity, and solutes migrate faster in silica gel 40 compared to silica gel 60, and they migrate much slower with silica gel 100 compared to silica gel 60. So in a silica gel, As the pore size decreases, the migration is faster. As the particle size decreases, the resolution between two spots increases. You should understand the difference between pore size. Pore size is the angstrom, 40 to 150 angstrom, and the particle size will be given as micrometers. So as the pore size increases, the surface area for interaction decreases. A large surface area results in greater contact or interactions with the analyte. So, thin layer chromatography is, if the way it is done is, either you can make the layer or pour thin layers of a slurry of silica gel or alumina onto a glass plate or any inert material. But nowadays, all the silica gel plates, you get commercially available plates of any thin layer that is required. So initially, the sample is spotted 1 centimeter away from the edge of the plate, and you should make sure that the spotting that you do, your spot line is not immersed into the solvent. If it is immersed into the mobile phase, your separation, your spot will go backward. Then you place it in a chamber which is equilibrated. Okay, so which is equilibrated with the solvent. Place the silica gel plate into it, close the silica gel, the chamber, and allow the chromatographic plate to develop. So here a series of spots form, and then once the spot forms, we always co-run the standards and we compare the samples in the mixture with the known substances, that is the standards. We measure the RF values just like how we measure it for paper chromatography. And if they are colored compounds, you can identify them. If they are colorless compounds, we can use different detection reagents or different visualizing reagents to identify the compounds. So here is a thin layer chromatography setup where you have the thin layer chromatography chambers, you have the solvent boat, the plate with the layer of it at 0 time, and the solvent tank is generally covered. It's a covered tank, and after the separation, you see that the analytes have moved and separated. If they are colored analytes, you can see the difference in the color. Otherwise, you have to use the techniques very similar to paper chromatography to identify these spots. So to prepare the chamber, you take a jar with a tight fitting lid, add enough of the developing liquid in the boat at the bottom of the jar. Close the jar tightly and allow the TLC chamber to be saturated with the solvent. If you do not allow the chamber to be saturated with solvent, you will see that your solvent front will be skewed. It will not be moving parallel to the edge of the TLC plate. Then once the plate is developed, the spots have to be identified. If they are colored, you can just outline them with pencil. If no spots are visible, we need to use a visualization technique. Generally, we can expose them to iodine, put the plate into a chamber containing iodine crystals, or you can visualize it under UV, in a UV chamber under a UV lamp, or you can use the different reagents for detecting the spots, such as anisaldehyde, aluminum chloride, antimony chloride, bromothymol blue, diphenylamine, Dragon-Dox reagent, gentian violet, or iodine vapor. So different visualization techniques are available. And then You interpret the data. How do you interpret the data? Just like paper chromatography, it is interpreted by calculating the RF, or the retention factor, and it is characteristic for a given compound on a stationary phase. The RF values can be compared with the RF values of the standard. So in the RF is given by distance traveled from start to the center of the substance spot, and distance from the start to the solvent front. Very the same as that of paper chromatography. So here is a separation of black ink on TLC. And then you have a technique, as I said, called high performance thin layer chromatography, which is the automated version of thin layer chromatography. That is the conventional thin layer of chromatography. And it is much more reproducible, accurate, and easy to perform, because the spotting is automated, the detection is after spraying can be automated. You can do a densitometry of it. So this is how a HPTLC works. You have a sample with the standard preparation. You have the pre-coated plates which can be activated, and you have automated sample applicators. So they will apply the sample, the precise quantity in the precise location, that is in a precise diameter. Then it is developed as usual in the chromatographic chambers, but that is done, and then the detection and scanning of the spots is done by the automated scanners. So you can develop it, and you can detect it with the scanner, and you can do the documentation. So it is just the automation of many of the techniques, that is many of the manual techniques in HP TLC. So you have automated applicators where the automation goes to the level that only you can spot only 0.1 to 0.2 ml. You have the Camag Nanomat or the Linomat, where it spots automated using a syringe 1 microliter. And then you have the automated TLC sampler, which is for a large number of samples. It takes it from the rack and continuously spots the TLC plate. So you have the automatic applicators. So here is the HPTLC of an amino acid of a plant which has been separated. And as we said, you can scan it, and you can find and quantitate the amount of the amino acids, because this is a photodiode array scan of the samples. The differences between TLC and HPLC are: in TLC, you can use either handmade or pre-coated. In HPTLC, we use only the pre-coated. So therefore, they are uniform, you have a uniform layer. So the selectivity and the resolution is good. The thickness in TLC is about 250 millimeters, but here we use very thin layers, 100 to 200. The particle size ranges from 5 to 20 micron, and here it is even smaller. So the smaller the particle size, the higher is the resolution. You don't need to pre-wash the plate in TLC, but in HPTLC we do a pre-wash. The application is either manual or semi-automatic. In HPTLC, it is semi-automatic or automatic. The shape of the spot in TLC is usually a circular. In HPTLC, depending on which spotter you have used, you can get a spot or a band. Spot sizes are very precise. Sample volumes are very low in HPTLC. The number of samples you can do in HPTLC are large. So the distance for development is very short because your particle size is very small, and the time depends on the mobile phase, and in HPTLC it is the. But the most important is that in HPTLC you can get reproducible results. Now we go to column chromatography, just the basics of column chromatography, because when you understand this column chromatography, it will be much easier when we discuss for you to understand high performance um, liquid chromatography, that is HPCLC. So quickly we'll go through. In column chromatography, as I explained, in the column, the stationary phase is packed into a column, and the mobile phase can either be a liquid or a gas. And according to the mechanism of separation that we have discussed earlier, five major types of separation are identified for column chromatography. These include, we have talked about adsorption chromatography. So here the stationary phase is a solid and the mobile phase is a liquid. The solutes move at different rates according to the force of attraction. Partition chromatography, this is a thin layer. It is the partitioning between two liquids, and the mobile phase is a liquid or a gas. Ion exchange, it is the separation because of the charge differences in the charge. The stationary phase is a resin carrying the charge, and the mobile phase is a liquid containing electrolyte. Molecular or size exclusion or gel permeation, a porous gel, and the mobile phase is a liquid. And affinity thing is a solid on which we have specific molecules, and the mobile phase is a liquid. So in column chromatography, the flowing gas or liquid continuously replaces the saturated mobile phase and results in the movement of A through the column. So if this is the column and it is packed with these particles and the analyte is placed here, the analyte moves along the column to be separated into the particle. So as the particles move or the analytes move through the column, it assumes a Gaussian concentration profile as it distributes itself between the stationary phase and the mobile phase. In TLC also, if you see, if you have a spot and the scanning is done, we have seen that even in TLC, you get the Gaussian distribution. So in column chromatography, as the solvent moves, it carries the analytes to form, to distribute the analyte between the stationary phase and the mobile phase in a Gaussian concentration profile. So this is what happens in the column chromatography. Each component has a different distribution coefficient and thus spends different times in the stationary phase and in the mobile phase. And as time goes by, you will see that the separation takes place. The analytes which spend less time on the stationary phase and more time in the mobile phase will elute first, whereas analytes like the red one spend more time in the stationary phase and less time in the mobile phase. So this is how progressively the separation takes place, and because of the partitioning or the ion exchange, you get a Gaussian distribution. Traditionally, in the laboratories, many of you might have done silica gel or alumina columns, where we use open columns. We fill the column with the stationary phase, and then we elute with the mobile phase under gravity, that is atmospheric pressure. But this has now been automated, and this is what we call as high performance liquid chromatography. Open column chromatography can be compared to thin layer chromatography, and high performance liquid chromatography can be compared to the automated version, that is the high performance thin layer chromatography. So in column chromatography, this is how in the open column chromatography, you fill a column, you put the analyte, and then you allow the mobile phase to carry the analyte and its residence time in the stationary phase, and the mobile phase will give you the separation. A similar separation occurs with size exclusion chromatography also. So in column chromatography, what we need to remember are some of these definitions. Solvent, which is the mobile liquid phase with no affinity to the stationary phase, and it has no effect on the solutes. It is inert. That means a chemical reaction cannot occur. So you cannot put a carbonate and an acid and carbon dioxide being produced. The mobile phase and the stationary phase have to be inert. The developer is the mobile phase, any liquid with more affinity to the stationary phase. The effluent is any liquid that passes out of the column. The eluent is any liquid that has a lesser affinity to the stationary phase than solutes, but is capable to move them out of the column. The eluate is the fraction of eluent containing the analyte, and the retention volume, similar to the retention factor VR, or the retardation volume, is the volume of the mobile phase that passes out of the column before elution of a specific substance. In the elution from the column, we can change the mobile phase concentration, or we can keep the mobile phase concentration the same. When we keep the mobile phase concentration throughout the elution for the complete experiment the same, it is known as an isocratic elution. That is, addition of a solvent mixture of a fixed composition during the whole process. You have a gradient elution where you can change the concentration of the eluent as the separation is taking place, and you can use linear gradients or you can use stepwise gradients. In the class on HPLC, detailed explanation of gradient elution, the continuous and the stepwise, will be discussed. So there are several factors in column chromatography which affect the efficiency of the separation, and these include particle size of the solid stationary phase, the column dimensions, the uniformity of packing, column temperature, the eluting solvent, the solvent flow rate, the continuity of flow, the condition of the adsorbent, and concentration of solutes. Here, the effect has only been summarized, but in HPLC, the details will be discussed. So, particle size. As the particle size, just like TLC, as the particle size decreases, the resolution increases. In column dimensions, as the column size or the length of the column increases, the efficiency increases, but the efficiency increases when the length of the column and the width decreases. So if you have a column with 4.6 millimeters internal diameter and you have a column of 2.1 millimeters internal diameter, the efficiency of separation or the resolution in the 2.1 millimeter column will be far better than the 4.6. Some separations are better at higher temperatures, so the columns are placed in an oven to increase the temperature. So the eluting solvent composition also plays a major role. Solvent flow rate, the flow rate when it is uniform and much lower, it gives better resolution, and the flow has to be continuous. and so therefore we use the pumps, whereas in the lab the flow is not continuous. We have a reservoir and we keep adding the solvent. So, one of the important things in column chromatography, which tells you about the efficiency of column chromatography, is what is known as the theoretical plates, or the separation. The efficiency of the separation is described by the theoretical plate model of chromatography. So here the plate model assumes that the chromatographic column is divided into separate layers, and these are called the theoretical plates. For example, if this is the column, we assume that the column is divided into several increments, thin increments, and these are known as the plates. Separate equilibrations of the sample between the stationary phase and the mobile phase occurs in these plates. The analyte moves down the column by transfer of equilibrated mobile phase from one plate to the other. Please remember that these plates in a column do not really exist. They are a figment of the imagination, but they all dictate to us the efficiency of separation. So how is this thing? Here, the number of theoretical plates is a measure of describing the column efficiency by stating the number of theoretical plates n in a column, or by stating the plate height or the height equivalent to a theoretical plate. So here, h is the theoretical plate height. The theoretical plate height is the distance between the plates. The length of the column is the length of this column. So the number of theoretical plates is equal to the length divided by the theoretical plate height. And the height equivalent to a theoretical plate TEP is given by the length divided by n. So as the HETP decreases, the efficiency of the column increases. So this is very clear, because if you have a higher number of n, that is the number of plates over here, the separation increases. The number of theoretical plates that a real column possesses can be examined by a chromatographic peak after elution, which when when I explain high performance liquid chromatography, it will be discussed in detail. This is just a prelude to the efficiency, the resolution, and the selectivity that are used in column chromatography, in the automated column chromatography. The same type of concept can be used for TLC, that is the theoretical plates. So this finishes the basics of column chromatography, and it is a prelude to the high performance liquid chromatography, which is an advanced technique. So once you have known column chromatography, it is very easy to understand the automated column chromatography. So the next class, that is tomorrow, will be on UV visible spectroscopy, and then it will be microscopy, followed by the high performance liquid chromatography. This is the order in which the classes will be taken, and tomorrow's class is between 4 and 5 p.m. and on Monday and Tuesday, my class will be between 11:30. The webinar starts at 11:30. So we will talk about microscopy, and we will talk about high performance liquid chromatography under the instrumentation technique.